Hi, I'm Jake Welby from the GRASP Lab at the University of Pennsylvania. Today I will discuss our work, Dynamically Feasible Task Space Planning for Underactuated Aerial Manipulators. Today, over 2 million robotic manipulators are in use around the world. However, virtually all of these manipulators are anchored to a point on the ground, limiting their workspace, flexibility, and independence. Research on mobile manipulators has attempted to broaden the scope of tasks that robots can complete. However, they are still limited by the types of terrain they can traverse and their limited agility. Many critical tasks also remain simply out of reach for ground-based mobile manipulators. In disaster scenarios, terrain may be simply impossible to traverse on wheels or by foot. In this famous 1932 photograph, men constructing a skyscraper take their lunch break, hundreds of feet above the city. Yet even today, humans must still work in these dangerous environments because robots are unable to operate there with sufficient performance. Turning to nature for inspiration, we see a hummingbird precisely maneuvering its beak while flying, in order to draw up nectar from the tiny hole in this feeder. The hummingbird is able to operate anywhere, regardless of terrain or elevation, and demonstrates an incredible combination of agility and dexterity. Our goal is to create robotic aerial manipulators with these same abilities. Many early aerial manipulators used quadrotors with rigidly attached grippers, performing tasks like object transportation. Early examples that included an arm often ignored the complex dynamics of the coupled system, limiting aggressiveness and accuracy. Recently, there have been two notable trends in aerial manipulation. The first is a move towards fully actuated vehicles, which are able to decouple rotation and translation, increasing maneuverability. The second is the use of highly redundant manipulator arms, which, like a macro-micro manipulator, can quickly compensate for error as the underactuated vehicle slowly and imprecisely tracks a dynamically infeasible reference. Both these advantages have their benefits, but they come at a price. Namely, thrust is precious, and to spend it supporting the weight of additional heavy actuators makes it unavailable for dynamic maneuvers, also reducing the severely limited flight time. Therefore, we choose to work with underactuated vehicles and arms with only the minimum number of joints necessary to complete the task. However, since we cannot control all degrees of freedom of an underactuated system directly, it is critical to plan system trajectories which respect the system's underactuation. Our solution is a method which takes a desired trajectory for the end effector and determines the family of system trajectories which will achieve this task without violating the underactuation constraints of the system. Most importantly, we do this without making any quasi-static or near-hover assumptions, so that our robots can perform highly dynamic maneuvers without sacrificing accuracy. Prior work has tackled some simpler cases of this problem. However, all prior approaches made very restrictive assumptions, such as limiting the approach to a 2D system only, assuming a constant velocity for the end effector, or only working with robots with specialized geometry, such as those where the arm is attached at the center of mass, which may be unrealistic or impractical in many cases. In this work, we remove all of these assumptions and solve the general case for an underactuated aerial manipulator in full 3D, equipped with an arm of arbitrary geometry and any number of joints. The first tool we leverage is differential flatness, which allows us to find a minimal and unconstrained representation for the dynamically feasible trajectories of the system. The trajectories of an underactuated system, represented in the state input space, must satisfy the differential constraint of the dynamics, making planning challenging. But for differentially flat systems, we can map the constrained trajectories in the state input space to smooth curves in what is known as the flat space, where the only requirement is smoothness. To do this, we must determine some flat outputs y, from which we are also able to fully reconstruct the state and inputs from its derivatives using the dynamics. We first demonstrate that the system's configuration manifold Q is a fiber bundle. All this means is that it looks locally like the product of two other spaces, namely the shape space S, which specifies the direction of the thrust vector, and the fiber space Y, which captures all remaining degrees of freedom, namely the position of the center of mass, and the joint angles, including what we call the virtual joint, which captures the remaining degree of freedom of rotation around the thrust vector. Using the bundle structure, we can parameterize the configuration in terms of the shape and the fiber variables. Because the only external forces are gravity and thrust, we can solve for the shape in terms of the center of mass acceleration, ultimately using the local trivialization to reconstruct the entire configuration. Taking derivatives will also give us the velocities and inputs, and thus it is clear that the system is differentially flat with respect to the fiber variables, namely the center of mass and the joint angles, including the virtual joint. At this point, we can represent any dynamically feasible trajectory in this minimal unconstrained space. However, what we really care about is the motion of the end effector, not the flat outputs. We now ask how to impose a desired end effector trajectory on the system without violating the underactuation constraints. Let some suitable task outputs T describe the end effector's motion. For example, we might wish to specify the pose of the end effector in SE3. These task outputs are related to the system's configuration via the forward kinematic map tau. If the system were fully actuated, all that would remain is the inverse kinematics problem of determining a trajectory which satisfies this mapping. The problem is that for underactuated systems, not all trajectories are dynamically feasible. Therefore, we propose to look instead for a flat output trajectory which will produce the desired task motion, since all such trajectories are dynamically feasible. The appropriate task space for an aerial manipulator will depend on the number of joints in the arm. For 0 joints, we consider the end effector position and the vehicle yaw. For 1 joint, we consider the end effector position and the direction it's pointing. And for 2 joints, we consider the full pose of the end effector. The planning problem can now be formulated by introducing all necessary constraints. First are the forward kinematics of the system, which relate the configuration and the task outputs. However, we choose to use the bundle trivialization to reparameterize the configuration in terms of the shape and the flat outputs. We know that the flat outputs y are free to evolve arbitrarily. However, the shape must satisfy the thrust constraint from the differential flatness section, which relates the shape to the center of mass acceleration. The first constraint contains no derivatives, but the second does, and so together these form a differential algebraic equation. We show that we can reduce this DAE to a differential equation, which governs the evolution of the shape as excited by the given task trajectory. The solutions to this ODE will determine the solutions to the overall planning problem. For well-behaved systems, the solution to an ODE can be parameterized by the initial conditions. Thus, there are infinite solutions to our planning problem, and each solution corresponds to a choice of the initial thrust direction and rate of change. However, we must select one solution, so we choose to optimize over all shape initial conditions, solving the corresponding initial value problem in order to evaluate a running cost similar to the familiar minimum snap cost used for standard quadrotors. We begin with a random initial guess and converge to the optimal solution. With only 4 decision variables, we can easily solve this optimization problem for an entire trajectory in just several seconds. Furthermore, our approach is an anytime algorithm, ideally suited for real-time planning. Even if the optimization must be terminated early, the current guess is guaranteed to be both dynamically feasible and achieve the task, even if it may be suboptimal. We have shown that the planning solutions are governed by a differential equation. However, some differential equations have unbounded solutions or escape to infinity in finite time. If that occurs for our system, then even some mundane task trajectories could require unbounded internal motions, which will be physically impossible to perform. Fortunately, we are able to identify 2 sets of criteria on the system geometry which prohibit poorly behaved internal dynamics. First, we show that if all axes of the system intersect at a common point, the internal dynamics resemble a spherical pendulum and are stable in the sense of Lyapunov, so finite time escape cannot occur. Second, we show that when the center of mass is fixed in the end effector frame and can be determined directly from the task outputs, then the internal dynamics vanish and the task outputs become another valid choice for the flat outputs of the system. These criteria will substantially inform the design of future hardware platforms. We now demonstrate the entire approach in simulation for 3 different tasks, each requiring an aerial manipulator with a different number of joints. First, we demonstrate an aerial manipulator with a body-fixed gripper acquiring an object moving quickly along a curved path, demonstrating the usefulness of agile and dynamic manipulation. We then demonstrate an aerial manipulator with a 1 degree of freedom arm, spray painting a design on the curved surface of a water tower. For high precision tasks like this one, dynamic feasibility is absolutely vital to make it possible for the system to perform accurately. Finally, we demonstrate a pick-and-place manipulation task, performed by an aerial manipulator with only 2 joints in its arm. By leveraging the agility of the vehicle itself, we are able to achieve full 6 degree of freedom manipulability, even though the arm has only 2 joints. In conclusion, this work presents 4 main contributions. First, we demonstrate that all underactuated aerial manipulators are differentially flat, regardless of their geometry. Second, we develop a method for planning dynamically feasible system trajectories to achieve a desired task, considering the full dynamics without any quasi-static assumptions. We then show how this formulation can be used in an anytime algorithm to select the optimal solution according to a running cost. Lastly, we determine criteria for the geometric design of aerial manipulators, which will ensure that the shape remains bounded throughout any task trajectory. Looking ahead, we will integrate our planner with closed-loop tracking control for practical implementation. We will also develop hardware platforms capable of highly dynamic maneuvers in order to perform tasks like throwing and catching. Finally, we hope to generalize this approach to other underactuated systems. Thank you so much for listening, and I'm happy to answer your questions.